I'm Marlyse. I'm a fifth-year PhD student at MIT, and I study risk-bounded autonomous systems. Specifically, my research is focused on autonomous agents that are learning about their models in the world. This problem was really fueled by environments where you have a system operating where risk and safety is really important, but gathering data is expensive or costly. One of the domains we're working in is energy, specifically like energy processing plants. So when you think of an autonomous system, it doesn't necessarily have to be a robot driving around the ground. It can be sort of any computer that's making decisions on its own. And so we are looking at kind of autonomously actually controlling an energy plant. Safety is important, and I think the idea is how can we take some of the safety that the operators are already doing as a human and put some of that into the autonomous system to help. So for example, the way the plant operates, it's a human operator that's setting the limits of how the machine is, how the different processes are running and setting the control limits and things. And so they're using their best judgment on what are safe levels for different variables depending on the environment and the output and all of those other things. So how can we take their sort of institutional knowledge of what does it mean to be safe, what are the limits we should watch out for, and how can we turn those into mathematical constraints for an autonomous system to understand, so that ultimately the human has to think less about that and more about things that humans are really good at thinking about. One of the things that we're interested in saying is, can you learn a model of an agent's behavior from previous information? Can you plan with that model of an agent's behavior in a way that is safe? Can you understand the uncertainty of the behavior that you learned or that another system learned? And then if you discover that that model is no longer sufficient, either due to the fact that the environment has changed or the fact that the agent was just underspecified or something breaks, can you then explore locally in your environment to kind of redevelop a better model for the agent operating in the world so it can continue its task? The two domains that we're looking at, one of them is energy companies, so working with natural gas plant data to try to see if we can use our system to safely control the plant. The other aspect is sort of very different, but similar ideas. There's a game that was developed originally in 1993. It's like an old ROM game called The Incredible Machine. Basically in the game, as a user, you have to sort of put together a Rube Goldberg machine to achieve some sort of goal. I think one of the things that makes humans so good at this game is that we're able to sort of experiment with the components and then quickly learn from what we experiment to then achieve the goal in the end. So you put some components on the screen, you run the mechanism to see if it achieves the behavior you want. If not, you're able to quickly say, oh, here's what I need to do to make sure that the behavior I want is achieved. And so having an autonomous system do the same sort of experiment test and update your model is what we're trying to do. And so the Incredible Machine game is just kind of a fun test bed for that. One of the things I really like about being in the MERS group is it's very application focused. So most of our projects come from industry sponsors where they have a very specific domain or problem instance that they want solved. Personally, for me, I think that's really rewarding when you're working with people who are trying to solve a really concrete problem, a problem in the world, and then you can apply our technology to it.